Hello and welcome to this calculus video. Today we will be discussing continuity.
Math 112.
In the non-math world, we say something is continuous if it is an unbroken or uninterrupted whole. We can apply this concept to the graph of a function. Let's look at these two examples. We see that the graph on the left is made up of one smooth piece. You could draw this graph without removing your pen from the paper. The graph on the right, however, is made up of two pieces. The line is broken, so we'd have to lift our pen up if we were sketching it. Like Justice Potter Stewart, you may be able to look at a graph and determine whether it is continuous, but you might not be exactly sure how to describe the property mathematically. Using the language of limits, however, we can express continuity precisely. A function f of x is continuous at the point x equals a if the limit as x approaches a of f of x equals the value of f at a. We can break this down into three pieces. F of x is continuous at x equals a if 1. The limit of f of x exists at x equals a, 2. F of x is defined at x equals a, and 3. These two values are equal. This is a precise mathematical definition of what it means for a function to be continuous at a point. A point where a function is not continuous is called a discontinuity of that function. Let's apply this definition to a few examples. The first graph forms a single unbroken line. This function is continuous everywhere. The second has a little hole at x equals 0. The function is not continuous at x equals 0 because the value of the limit there is not equal to the value of the function. So the function fails requirement 3 in the definition of continuity. If the limit of a function exists at a point, and the function is defined at that point, but these two are not equal, then we call it a removable discontinuity. The third example has a function which jumps at x equals 0. Because of this jump, the limit of the function does not exist at x equals 0, so it fails requirement 1 of continuity at 0. If the limit of a function fails to exist because the left and the right limits both exist but are not equal, then we call it a jump discontinuity. The fourth example has a vertical asymptote at x equals 0. Therefore, the limit does not exist there, so the function fails requirement 1 of being continuous. If a function has a discontinuity because it has an asymptote, then we call it an infinite discontinuity. Finally, we have example 5. This function is hard to draw yourself, and even Desmos gives us something strange. Near x equals 0, the function is oscillating so fast that the line starts to merge because of its thickness. With this in mind, the function has no limit at x equals 0 because the graph is not settling down and approaching a y value. Again, we fail requirement 1. But here it is because the function acts wildly near x equals 0. Such a discontinuity is called an oscillating discontinuity, and every discontinuity that isn't a removable, jump, or infinite discontinuity is called oscillating. We have defined continuity using limits, and just like with limits, there is a one-sided version corresponding to one-sided limits. A function f of x is left continuous at x equals a if the left limit of f of x at x equals a equals the value of the function at x equals a. There is also a definition of right continuous, but I leave that as an exercise for you to write out. Let's look at an example. This function is called the ceiling function. It takes a number x and returns the least integer greater than or equal to x. In other words, it rounds up x to the nearest integer. For instance, the ceiling of 2 is 2. The ceiling of 0.6 is 1. The ceiling of 3.1 is 4, and the ceiling of negative 1.5 is negative 1. The ceiling function has jump discontinuities at each integer, because the left and right limits there are not equal. However, the left limit does equal the value of the function. Therefore, the function is left continuous at every point, even though it is not continuous at the integers. Left and right continuity are much less important than two-sided continuity, which we usually just call continuity, but they do allow us to state an important definition. A function f of x is continuous on the closed interval a to b if f of x is continuous at every x in the open interval a to b, is left continuous at x equals b, and is right continuous at x equals a. Verifying a particular function is continuous can be a lengthy process. For a function f of x, we would need to show that the limit of the function exists everywhere and is equal to the value of the function. Luckily, if we have a function built out of continuous functions using nice operations, then we tend to get a continuous function out. For example, polynomials, root functions, trig functions, inverse trig functions, exponential functions, and logarithmic functions are all continuous. Also, if we add, subtract, multiply, divide, or compose continuous functions, then we get a continuous function out, wherever that function is defined. Let's go back to our initial idea of a continuous graph, which I described as a graph you could draw without taking your pen off the paper. Suppose we have a continuous function f of x with f of 0 equals 10 and f of 2 equals 6. One interpretation of the can't take your pen off the paper quality is that every y value between 6 and 10 must be achieved by f as x varies between 0 and 2. Here are some different functions which do this. This intuitive property is wrapped up in our first major theorem, called the intermediate value theorem. Before I state it, I'm going to take a little detour into mathematical terminology. So far we have had some definitions involving limits and continuity. Definitions tell you what words mean, so they can't be true or false. By this I mean, continuous isn't either true or false. However, a statement that a particular function is continuous is either true or false. A theorem, by contrast, is a mathematical claim that has been proved. Theorems are often stated in the form, if something, then something. For instance, if a shape is a square, then it is a rectangle. Such statements are called conditional. The part of the statement before the then is called the hypothesis, and the part of the statement after the then is called the conclusion. Let's get back to the intermediate value theorem. Its general statement follows. If f of x is continuous on the closed interval a to b, and n is a number between f of a and f of b, then there exists a number c in a to b such that f of c equals n. Let's apply this to an example. Suppose we want to solve the cubic equation 4x cubed minus 6x squared plus 3x minus 2 is 0. There is actually a formula for the general root of a cubic, but if we don't know this formula and we can't see a factorization of this polynomial, we might be stuck. Let's introduce the function f of x equals 4x cubed minus 6x squared plus 3x minus 2. Notice this is the left-hand side of the equation that we're trying to solve. By plugging in, we see that f of 0 is negative 2 and f of 2 is 12. Also, our function f of x is a polynomial, so it is continuous. Therefore, by the intermediate value theorem, we know f of x obtains every value between negative 2 and 12 as x varies between 0 and 2. In particular, f of x must attain the value 0 at some point between x equals 0 and x equals 2. We don't know the exact x value that works, but we do know that there is one between 0 and 2. So, we haven't solved our equation exactly, but we do know there is a solution between x equals 0 and x equals 2. That's all for now, folks. In this video, we defined what it meant for a function to be continuous at a point and classified various kinds of discontinuities. We also defined what it means to be left and right continuous at a point, as well as continuous on an interval. We learned that many familiar functions are continuous on their domains, and that we can combine continuous functions using arithmetical composition to form new continuous functions. Finally, we stated the intermediate value theorem and used it to find an approximate solution to an equation.
Math 112.